Hello, thank you all for joining IMPLAN's monthly webinar series. We do have a lot of content to cover today, so I will kick off today's presentation in about 1 minute. So just to give enough time for people to get in and settle. So 1 more minute and we'll get started. All right, once again, hello everyone and welcome to our August webinar. For those of you who are joining us for the first time, IMPLAN hosts a monthly webinar series on various topics with our education services team. We have an exciting topic today, regional trade in IMPLAN, models, data, and visualization. Regional trade data used in IMPLAN's input-output model is available for our users to explore in Data Library. This data can provide essential insights into a region's economic activities, needs, strengths, and weaknesses. It can be helpful for making decisions about resource allocation, understanding a region's economic health, discovering market opportunities, policy making, and much more. Over the next 45 minutes, we will explore how IMPLAN's trade data was conceptualized and sourced, as well as how it can be used to make better decisions and provide a deeper understanding of local economic conditions. First off, I would like to introduce myself. My name is Angela Slavacek. I am the Director of Education Services here at IMPLAN. Joining me today and presenting is the Academic Division Director and our economist, my colleague, Dr. Bjorn Markeson. Here at IMPLAN, we like to keep our webinars interactive by allowing attendees to pose questions live to our presenters. However, today's presentation will likely take close to 45 minutes, so we ask that if you do have a question related to today's topic, please utilize the question box in GoToWebinar. The Education Services team, which includes myself, will do our best to monitor the question box throughout the presentation. If you think you might want to ask a question, just make sure that you have your control panel open by hitting that orange arrow in the upper left portion of the pop-out window. At the conclusion of the presentation, if we do not get to answer your question within this time frame, we will personally follow up with everyone to provide a response. So with that, I will pass it off to Bjorn to get us started on this wonderful topic. Bjorn.
Excellent. Thanks, Angela. So before we get started, I want to kind of do a quick overview of what we're going to cover today. The first is what trade data is available in IMPLAN and where it is available in IMPLAN. So what type of, what is the form that the data is in? How can you access it? How can you use it? We also want to cover how IMPLAN's trade data is built. In other words, this isn't just some data that we're either pulling from another source or what have you, but we're building it, and how is that process used? We're also going to use IMPLAN Cloud and the data library to find where that trade-related data is, so you can get to it and use it in your own applications. And throughout the webinar, I'm going to highlight different use cases and applications of this trade data. Again, as Angela said, if any questions that do come up, please use that question box to ask them. So thinking about interregional trade in IMPLAN, to build accurate regional economic impact models, IMPLAN needs to have an idea of how much of a given commodity is brought in from other regions, shipped to other regions. And this is both for single region and multi-regional or MRIO IMPLAN models. They require estimates of a value of a given commodity shipped to and imported from other regions. These data are not readily available in a consistent and reliable format, so IMPLAN needs to build them. And to do this, we build county to county commodity trade estimates on a dollar value basis. So let's take an example. We look at Greene County, Wisconsin. It's a producer of both cheese and milk. Greene County uses their own milk and imported milk to produce cheese, some of which they ship to other regions, and some of which they consume themselves. All of these values are important in understanding how Greene County is affected by changes in the milk and cheese industry. So, getting into the example of $350 million of dairy and milk products that are needed for cheese manufacturing in Greene County, 68% of that is imported from other regions. In other words, they're shipping in milk to produce cheese. Nearly all of the dairy and milk products produced in Greene County are used as intermediate inputs in Greene County. In other words, Greene County is combining dairy and milk products from their county and from outside that region in their production. And then of the $1.1 billion in cheese manufacturing output in Greene County, 96% of that is exported to other regions. So, about 3% of it, 3.75% is consumed in Greene County, but the rest of it is exported. So it's important to, that piece is important to understand how Greene County is connected with the broader US economy. So we can see that interconnection here. Greene County ships cheese beyond their immediate region to major population centers all over the country. Here we're using a tool in IMPLAN's data library to visualize this distribution and interdependence. What we're seeing here are locations where cheese is used either as an intermediate input, say in producing frozen pizza, or in household consumption. So what do we see? We see a couple of different things. The scale on this is from the greenest regions, which are very low consumption of Greene County or trade in Greene County cheese, to red regions, which is very high value. We see a lot of that trade concentrated in the upper Midwest, Minnesota, Wisconsin, Illinois, and then population centers throughout the US, New York, Florida, Texas, Southern California, Arizona. We also see something else, which is that large swath of green across the rest of the country. So this is not a good that's being shipped to 1 or 2 or 3 specific locations, but also is being shipped much more broadly across the country. So it's both deep in particular regions, but wide across the country. And so on the left, we can see those 10 largest regions for that estimated trade value. And we see those in Illinois, Wisconsin, California, Texas, and Arizona. So this is giving us an idea of where that trade is going, where that cheese is being shipped to throughout the country. So again, these data are not readily available in a reliable and consistent format. So how do we build them? It's a good question. I'm going to dive in and talk about different ways of thinking about estimating trade and then settle on how we do it. I don't want to just say, we use a doubly constrained gravity model, wave my hands and move on. So I'm going to walk through what that means so you have a better idea of what this data is, and then get back to practical applications. So how do we derive this trade data? So IMPLAN uses a doubly constrained gravity model to estimate trade flows for all IMPLAN commodities between all counties in the US. And the two pieces that it's constrained by are commodity supply and commodity demand. We know where goods are produced, we know where they're consumed, either as intermediate goods or final consumption, and we're using this trade data to match those up. So the trade-based gravity model used by IMPLAN is conceptually adopted, as the name suggests, from Newton's law of gravity, right? So in this case, gravitational attraction between two masses is directly related to the size of the masses, and then inversely related to the distance between them with some gravitational constant g. So you've got two pieces, two masses, mi and mj, and then the distance between them, and that's driving that gravitational force. And we can think of trade in similar ways, right? We can think of the size of supply and the size of demand, and then the distance between them. This was first suggested to use in an input-output model by Leontief and Strout in '63. Over the last 60 years, the gravity model has been widely and effectively used to estimate trade flows in a variety of circumstances, including by the Federal Highway Administration and a number of other applications. So how do we derive this data? Or how do we think about trade? A first step way to think about trade would be for a given region to export to each other region a proportionate share of the good produced. So the trade between region I, the producer, and region J, the consumer, is that proportion of J's consumption of total production. So we're going to ignore distance for right now. If region J has 10% of all demand for a commodity, then each region that produces that commodity will send 10% of their production to region J. In this case, region 1 and 2 each send 10% of their production to region J. And that's just what that first equation is showing, right? That proportion from I to J is demand in J over total demand. We can translate that from a proportion to a quantity of goods, which is what that second equation is, where O sub I is the total supply of the commodity originating in region 1. So all that's doing is translating that from a proportion to actual quantities. But here all we're seeing is that each region ships out a proportion of the total consumption in the demanding region. So Isard and Carroll and Bevis showed that the effective distance on trade is not necessarily uniform. So once we introduce distance, the solution suggested by empirical studies is to raise that distance variable to some exponent b, thereby giving larger distances a greater proportional deterrence than small distances. The question of what value to give that exponent can be difficult, and we decide that during the calibration of the model, and we'll discuss that a bit later in this presentation. But in this case, if regions 1, 2, and 3 all produce the same amount of a commodity, region 1 will ship the most to region J, followed by regions 2 and 3 respectively, because the distance between them is different. The degree to which they're different is dependent on their distance and B. So, and because it's an exponential effect, the further away a region is, the more of a deterrence you see. And that's what these equations show. And on the right-hand side, we've just simplified that and rewritten that to make it easier to read. So essentially what we said is, okay, distance matters, and really large distances matter a lot. The further away you get, the harder it is to overcome that distance. In a number of studies, experience showed that these formulations can often overestimate the volume of short hauls. Again, Isard and Carroll and Bevis showed this. And this led to a reformulation of the gravity model to account for all competing sources of demand. And so we took the numerator on those equations and divided it by the sum of all trade in the economy. So in other words, what this is doing is this is helping to account for and mitigate those shorter hauls. So we're taking into account all of the shipping going on in this economy. we're going to do a little simplification. We know that, demand is constant for all regions. The total demand is constant for all regions, can be pulled out. We summarize A sub I is the inverse of the sum of the distance deflated demand in region J. So since the sum of all the proportions is 1, we can derive a singly constrained model where the sum of all trade from region I is equal to the total supply in region I. So at this point, we have a region-to-region commodity trade estimates constrained by that supply. So in other words, we know what that supply looks like. And then it's also necessary to constrain that system so that all trade flowing into region J is equal to that region's total demand. So in other words, we've constrained it by the supply. We need to constrain it by the demand. The known demand is divided by those estimated total inflows. So we're almost there. Each first round supply constrained estimate of trade to region J is then multiplied by B to obtain the first round demand constrained estimates of trade. And we're going to start iterating this, right? This iterative process is then repeated until the trade estimates are doubly constrained. That is, until all supplies go somewhere, including trade within the same county, and all demands are fulfilled. So when that computation comes to an end, each trade flow will have been multiplied in succession by 1 or more ratio A sub I, so on and so forth, and 1 more ratio B sub J, J prime, so on and so forth. And we get this equation where that trade between regions I and J is a function of 5 different things, or 4. A sub I, B sub J can be thought of as that derived gravitational constant, right? So that's the gravitational constant in here. We've got O sub I, which is going to be the total commodity produced in region I, D sub J, the total demand in region J, and then the distance between those two locations. So the AB is constraining on using that gravitational constant to constrain and to build out the amount of trade flowing between those regions given a distance. So from a application perspective, right? So we're thinking of what do we know? Well, we've derived a constant, we have that. We know how much of a good is produced in a region, and we have from our tables the demand that is going to be needed in that region. So the next piece to think about when we're thinking about calibrating that model is to think about distance. So now we have that theoretical structure for deriving those trade values. We're going to bring this back into the real world and build some practical data into it. And the first piece we're going to talk about here is distance. While distance can seem like a reasonable approximation of spatial separation between any 2 points, it's not always the case in economic transportation, right? So if I draw a straight line between 2 places, that's not necessarily representative of how far those places are in a practical sense for engaging in economic activity. Some modes of transportation have relative advantages, such as rail or water transportation. Others may have disadvantages. And so we can think about this with a practical example, right? So if we think about the highway distance between Denver and New Orleans, it might be shorter than the highway distance between St. Paul and New Orleans, right? But barge transportation on the Mississippi makes it more efficient to ship grain from St. Paul rather than Denver, right? So we don't have a lot of grain being shipped from the middle of the country to Denver and then to New Orleans. It's shipped to St. Paul, the Twin Cities, and then sent down the Mississippi because it's a more efficient method. So the straight line distance, or the as the crow flies distance, might be longer from St. Paul to New Orleans, but the practical economic distance is shorter. So how do we think about that? How do we take that into account? So what we do is we use an integrated intermodal transportation network modeling system from the Center for Transportation Analysis at Oak Ridge National Laboratory. And this accounts for tolls, congestion, and other factors that it derives at travel impedances between each county centroid to every other county in the US by mode of transportation. So in other words, what that is how much is travel impeded between regions, not just in general, but by mode, by truck rail, by truck water. The weighted averages of these serve as this weighted averages based on the mode mix that we get from the commodity flow survey, which I'll talk about in a second. That's where we get our distances, right? So these distances that we're talking about are not just drawing a line on a map. It's not just using highway distances between 2 points. It's a much richer data set that takes into account modes of transportation and the distance and the effective economic distance that those imply. So we pull additional data from the commodity flow survey as well as the freight analysis frameworks. One is on mode of transportation by commodity. The commodity flow survey and the freight analysis framework tables show the proportion of total commodity value, tons, ton miles that were transported by various transportation modes. This table of shipment mode provides the basis for our decision as to which of the impedances to use in the calibration of the model, or in other words, the weighting to give various modes of transportation by commodity. So in other words, the model doesn't assume that all commodities are shipped in the same way. We use a weighted structure to make that more accurate. And then after determining the appropriate value and functional form for that distance, we need to determine the appropriate value for B. And again, we're relying on data from the commodity flow survey and the freight analysis framework, and using data on the value, tons, total miles moved by each commodity. And we start with the previous year's estimate for B, rerun the model, adjust it so that adjust beta for the B for each commodity until the sum of those trade flows for that commodity for all regions are suitably close to that national average movement of that commodity as reported by the commodity flow survey. So we're using that commodity flow survey as a benchmark to essentially ground truth that model to make sure that we are accurately representing that in the calibration process. A few key assumptions that to keep in mind. One is that a fully defined gravity model can estimate trade flows between counties, and I think that walking through and understanding what we mean by the gravity model makes this a reasonable assumption, right? So that the degree to which goods are shipped from one region to another based on the supply and the demand of each of those goods flows from this gravity model. The second is that we can make these data sets talk to each other. This is a process that we run on an annual basis, and we've become really good at working with these data and making the standard classification of transportation goods data, commodity flow survey data talk to and bridge to the 500 IMPLAN commodities. And then finally, the commodity flow survey average ton miles moved is a good indicator of the average distance commodities travel from point of production to point of consumption. And we found through experience and general analysis that is reasonable as well. So now I want to talk about a couple of uses and applications. So we've gotten into the weeds of how this is built and where we're coming from when we're thinking about building these trade data values and ratios, and how can we use it? Well, the first way is to think about how IMPLAN uses it. So the county-to-county commodity trade data enter into our economic impact model in a couple of different ways. The first is to calculate regional purchase coefficients. So a regional purchase coefficient describes the proportion of each dollar of local demand for a given commodity that is purchased from local producers, with higher regional purchase coefficients indicating less leakage outside of the region and are going to lead to larger input-output multipliers. Prior to the development of the trade flow model, we used a series of econometric equations. This is derived from a 51 region multi-regional model. It's based on older data and an update of the pioneering work done by Karen Polensky. But the RPCs of non-shippable commodities were based on observed values. We found that the econometric RPC methodology, it's a statistical approach and it's susceptible to that estimation error associated with statistical analysis. But when we're thinking about what an RPC is, what a regional purchase coefficient is, it's rooted in that trade, right? How much of a good is, in order to understand how much of a good is used from local production, you need to have an idea of where all of the other goods can come from. So we can find this regional purchase coefficient data in IMPLAN. So if you're a cloud platform, we can go to the region details for a specific region. We can go to the social accounts, the industry balance sheet for commodity demand. And what this is going to give us is a set of regional purchase coefficients for commodity demand in a region for an industry. So here we're looking at surgical and medical instruments in Minnesota, and we're looking at the first column are those regional purchase coefficients. So I've sorted this by the cost of gross inputs. So a large expenditure is on wholesale services for commercial equipment and supplies. Almost all of that is sourced within the region of interest. So a very high RPC. Not much is being shipped in from outside of Minnesota, which is not particularly surprising. We can also see some goods that are not produced locally. Surgical appliances and supplies, plastic materials and resins, synthetic rubbers are all very low regional purchase coefficients, and those are goods that are being shipped in. That's a trade flow that's coming in from outside of Minnesota into the region and giving us a lower RPC and more leakage outside of the region. One way to think about these RPCs is they're dependent not just on those trade flows, but upon the region, the size of the region you're looking at. So a very small region, so if we draw a circle conceptually, like around a zip code, almost all of that, the inputs to any sort of production in a given zip code are likely going to come from outside of that zip code. A zip code isn't an economy. And so the number of industries that are, that have a lot of suppliers within exactly the same zip code is going to be pretty small. So your RPCs, your regional purchase coefficients, your economic your input-output multipliers are going to be relatively small. as you draw that circle larger around a metro area, around a state, around 4 or 5 states, the amount or the quantity of the goods that are able to be purchased within the region is going to go up. More of those products are sourced within that region, less need to be imported from outside of it. Taken to kind of the first step extreme, if we think of the United States as a whole, everything is purchased within the US as a whole, except those things that are imported from outside of the US. So that regional purchase coefficient for domestic goods is going to be very high. The second way that IMPLAN makes use of this trade data and can be used by our users is through multi-regional input-output modeling. So I'm not going to go into the details of how to do MRIO right now, but just to kind of touch on what the trade data allows for. So if I want to know how, so I could think about, I was just on vacation up in northern Minnesota in St. Louis County, which is the major producer of iron ore in the US. So these mines are heavily dependent upon the broader economy. The economy in that region is dependent upon how that industry is doing at any given time. So if we wanted to look at the economic impact of a change to the iron mining industry in St. Louis County, that would be one thing. But it's so large that it has a broader effect. It has an effect on the rest of Minnesota. It has an effect on parts of northern Wisconsin. And so if I wanted to trace that impact and say, if there's a 10% decrease in output value in iron mining in St. Louis County, how does that affect the rest of Minnesota? How does that affect Wisconsin? And I can use MRIO to do that. That multi-regional input-output allows me to trace those effects to the broader region. And we can see that both in terms of something like St. Louis County or changes in a metro area, right? Shocks to the economy in Charlotte have a broader effect on the region around it, and we can use MRIO to trace those effects. The other place that we can find trade data in IMPLAN is in the data library. So data library is included if you've purchased a State Explorer package, a national package, or have an institutional license at your university. Otherwise, it's something that can be added on or purchased independently. But what we're looking at here is a set or a number of sets of tools that allow you to look at the data that helps drive IMPLAN. And one of those is the trade data. So here, if we're looking at in the data library, we can look at first we'll look at the dashboard and we see the trade flow dashboard. So we can choose that trade flow dashboard. Here, we're going to look at the types of goods that are shipped to Snohomish County, Washington, which is the site of a large aircraft manufacturing facility. I've made a couple of adjustments to this. I'm looking at data for 2021, and in the 2023 dollar year, we're using the IMPLAN aggregation codes. You can also do this at the NAICS code level. We're looking for goods that are being shipped to Snohomish County, and we're looking at it coming from any state other than Washington, Alaska, or Hawaii. I'm keeping Washington out of it because there's a lot of local trade. I'm keeping Alaska and Hawaii out of it for ease of viewing on the next map. And then I'm also looking at trade that is valued greater than $500,000. So again, when we're building that trade flow data, what we see is that we estimate it down to a pretty tight dollar value. So I don't want all of those data in the data table. I just want the big trades. So this is how I'm filtering it. One way of looking at this is on a map. So what we're seeing here is that goods are pouring into Snohomish County from all over the US, right? This is not just a local manufacturing facility. It drives economic activity from coast to coast, right? So we aren't. The manufacturing facility is importing goods, intermediate goods, to be used in that county's economy, and they're pulling them from everywhere. What types of goods are we looking at? Well, we're looking at commodities from banks, but also aircraft engines from Hartford, Connecticut, automobiles from Alameda, California, electronic computer parts from Santa Clara County, California, and so on. So semiconductors from Washington County, Oregon, and Santa Clara County. So a wide range of inputs to that industry. It gives an insight not just to the volume of trade, but where it's coming from. And you can export this data, right? So you're not restricted to just the tool that we have. In the upper right-hand corner of Data Library, there's 3 vertical dots. You can choose download, and then you can pull this into any number of different formats, such as an Excel table. I can then use this as needed for further analysis to build out some tables and charts to help show and identify the interconnectedness of this region to the broader US economy. Another way of thinking about this is I was talking with some folks that were looking at wine in North Georgia. So North Georgia, the number of wineries, and they were talking about how they talk to the producers and they have an idea of where they ship to, and they wanted to see, did our trade data match up with what they said? So we ran the analysis. We pulled up the dashboard and looked at it, and it did match up because they were saying that most of the trade in wine. So here we're looking at wine and brandy being traded that originates in Georgia. And where is it going? Well, it's mostly staying in Georgia. It's mostly staying in the Atlanta region and northern Georgia. Some of it is would be shipped out to North Carolina, South Carolina, and Florida, as well as a little bit to Alabama. But what we're looking at here is a modeled prediction, right? So this is where it's important to talk to folks on the ground and ground truth this data, in the sense that what this is it's a modeled value. And let's say it is, for just the number of laws around the trade of alcohol is high. Let's say that it was illegal to ship wine from Georgia to Florida. Well, that wouldn't necessarily show up in the model. We haven't constrained it by legal shipping requirements. And so what this would be is this would be a predictive of where those markets could be if those restrictions were lifted. So this is telling you where that demand would likely go in a free and open market. So if you're talking to those producers and they're saying, well, we're not shipping to Florida, there's demand there that could be met using this particular product. There's another way we'll show one more way of looking at this before we wrap up. There's another way of digging into and kind of customizing these data pools, and that's using what's called an explorer. So we can explore that trade flow data. What this does is it pulls up a bit more of a technical interface that allows you to specify a particular set of data that you want to pull from our SQL databases. So in this case, I want to pull reconstituted wood products, particle board, produced in Beltrami County, Minnesota, and shipped outside of that region for dollar values more than $100,000. I can pull that, I get a full table, and I can export it. This has, the FIPS codes associated with it, so that allows us to tie it to specific geographies, and so you can export this into your own GIS for representation or analysis. One thing to point out is that this trade flow data as a data set is somewhat large. If you think about it, what we're looking at is trade between 3,000 different counties, so county to county trade. So that matrix would be 3,000 by 3,000 for each of 500 some industries or commodities. And so in a column format, you end up with about 2 trillion rows of data per year. So 2 trillion rows of data, we've got 20 years of data in data library. That's a lot of trade flow data. Can you export all of it? No, you need to kind of break this up into pieces. That's not a deliverable way of consuming it. So that's what the data library allows you to do, is to kind of really fine tune the pieces of data that you need from this to give you the insights you are looking for. So one final point. There's been a lot of talk in policy circles around semiconductors recently. So in semiconductor supply chains. And what does that mean in terms of the regions of the US that use semiconductors? With the trade data we've built, you can get a good insight into that, right? So here what we're looking at is semiconductor trade in the US. We can see that what we would expect is a significant amount of that trade is on the West Coast. It includes Texas, so California, Oregon, Washington, Texas, Arizona. But it's not just limited to those regions, right? So that trade is including Florida, it's including the Northeast, it's including the Upper Midwest, as well as North Carolina, Kentucky, Kansas, Alabama. So it gives us an insight as to where that trade is occurring. And to the best of my knowledge, there's no other easy to use tool to get this kind of reliable data-driven insight into regional trade. So if you want to learn more about this data or all the data and tools that we have in IMPLAN Cloud, I'll put up some information about how to schedule a personalized demo here in a bit. But I do see that we've got a couple minutes, and there's a couple questions. One question came in: can academics or researchers purchase a license to have access to these data? Yes. As I mentioned, the data library is either available for purchase outside of the IMPLAN input-output modeling tool, or it can be added to that modeling tool as an add-on. Or if you have a larger purchase, either at an institutional level, say at the university-wide, or you have a national plan, you have access to that already. Let's see. So what about international trade? It can't just be domestic county-to-county trade. So the U.S. Department of Commerce's Foreign Trade Statistics Series, the annual data set, it's non-lagged and is not a part of the gravity model estimations. So in other words, this gravity model is estimating those county-to-county trades for domestic production. And with that, I'll put up the information about a personalized demo. Again, any questions that we didn't have time to get to, since we are up against time, we'll have someone follow up with you directly on those questions to help you answer those. But again, if you want to talk about this in more detail or about anything else you've seen, you can go to implan.com/demo or email the sales folks at sales@implan.com. we'll kind of go through this data for you.
Yes, thank you so much, Bjorn, for the time today. If you guys want to schedule a demo, please reach out. We can schedule that for you. Otherwise, you can always find the recording for this webinar on our support site at support@implan.com. So if you have any questions, please reach out to your CSM. And with that, thank you so much, Bjorn, and thank you everybody for joining us today.
Thank you.